Okay, good day to all of you. So welcome to our online electrical engineering review channel, and we are on our power factor correction problems, which is under lesson 4, pole phase systems. So if you want to have the copy of the problems, you can go to the description tab, and then from the description tab there is a link that will transfer you to a Google Drive or sheet. Then from that Google sheet you can have those main problems and as well as the supplementary problems that you can practice. Okay, let us solve problem number 1. Let us read problem number 1 first. A 3-phase load draws 250 kilowatt at a 0.766 power factor lagging. It is desired to increase the power factor to 0.9 lagging. We need to find the power in kVAR of the capacitor which is needed. Okay, now in order to do that, we need to have the given first. The given is real power 250 kilowatt, which is constant all throughout. And then we can now get the angle theta 1, which is the inverse of the power factor, which is 0.766. This is from the formula. Power factor is equal to cosine theta. And then we can now have the theta here, the inverse of the power factor. So that it will become like this. The inverse of the power factor 0.766, which is 40 degree, and the angle 2, which is the inverse of the power factor at 0.9, which is 25.84 degree. Now we have here, if the answer is positive, it means it is in lagging condition. If the answer is in negative, otherwise it is leading. So our answer is in a positive form, which means both of them are lagging condition. Now we have the opportunity to substitute on our main formula, which is P tangent theta 1 minus tangent theta 2. And thus, by substituting all of the values and numerically, we can solve this problem. And using your calculators, the answer is 88.7 kbars. Now, we can now proceed to our next problem. Now, we will discuss problem number 2 under power factor correction. So let us read the problem first. It is desired to improve the power factor of a 230 volt 60 Hz 3-phase system from 0.7 to 0.92 lag. Now a Y-connected capacitor bank with a capacitance of 10 microfarad per phase is to be installed. What will be the kilowatt of the load? Okay, when you say what will be the kilowatt of the load, the required on the problem is the real power P. Okay, we have the given first. We have the 10 microfarad capacitor, the voltage 230 volt, and the frequency of 60 Hz. As we have mentioned in the first problem, we can get the angle displacement, or the angle, or the power factor angle rather, which is cosine negative 1 of the power factor, which is 45.47, and it is lag, so the value is positive. Theta 2, cosine negative 1 of 0.92. Since this is also lag, we have a positive angle as well, 23.07 degree. Now, from what we have discussed from the basic fundamentals, so just recall the basic fundamentals, that we have the QC is equal to VL squared over XC, but XC is 1 over omega C. So omega C will go to the numerator part. So the equation is VLL squared omega times C. Since we do not have, we have a frequency of 60 Hz, or if there's none, you can assume at 60, the omega is automatic 2 pi f or 377 radian per second. So you have 230 squared, 377 times 10 micro. We can have QC as 199.43 VARs. Now we have the opportunity to get the real power from this equation that we have discussed so far. QC is equal to P tangent theta 1 minus tangent theta 2. Rearranging the equation, we have P is equal to QC all over tangent theta 1 minus tangent theta 2. Just substitute all of the values of QC, theta 1 and theta 2 on this equation, or rather this equation, and thus the answer for real power is 335.63 watts. Now we can now move forward to the next problem. Hi, And hello once again. So we will conclude our discussion here on problem number 3, which is on the power factor correction topic. So before we do that, let us read the problem first. A 50 HP, 40 volt, 60 Hz 3-phase motor operates at a full load with an efficiency of 89% and a power factor of 0.85 lag. Now determine the capacitance in microfarad per phase of a Y-connected capacitor bank to be connected across the motor terminals to improve the power factor to 0.95 lagging. Okay, this is the solution, and I have some important marks here so that we can clarify further the problem. When you say a 50 HP, it means that is P out. Okay, the output power of the motor. And when you say 440, that is a line-to-line voltage. If you encounter these problems like a 50 HP or 100 HP, 440 volt or 220 volt 3-phase source, those values by default is output power and line-to-line voltage. So please do remember that, because you will encounter those words or phrases on the next few problems. So you have a default that is output and line-to-line voltage. Okay, now being so, we have here 50 HP output, efficiency, P out over P in, since efficiency is given, so you need, or you are required to get input power. By having P out over efficiency, you need to convert the 50 HP to watts by multiplying by 746. And you divide it by 0.89. Okay, our answer is 41,910 watts. Okay, this is from our last lecture, that we can now get the angles by having the inverse of the power factor, inverse of the cosine inverse of the power factor. So from 0.85, we have 31.79, and then from 0.95, we have 18.19 degree, respectively. So we have here the opportunity to get the QC, or the reactive power, by having P tangent theta 1 minus tangent theta 2, since all of the values of the angles, theta 1 and theta 2, and the power is already computed. Just substitute into the QC equation, and it will yield to a 12,204 var. And thus, we can now get C. Now, the connection is a Y connection. So, if that is delta, for example, you have a 3 here. But on our problem, we have Y connection. So, CY, or Y connected capacitor per phase. So you have QC all over omega line squared value of the voltage. So therefore, you have 12,204.0061 all over 377, 440. And please take note, the 377 here is from the 60 Hertz frequency. And computing the value of the capacitor in microfarad, the answer is 167 microfarad. Okay, thus it will conclude our discussion on power factor correction. So see you on our next topic, which is phase sequences, or phase sequence of your generators. See you, ciao, at maraming salamat.